class, we were looking at Monte Carlo learning. And the important formula that we used a bunch of times was this first formula for the average of n plus 1 things. So if you have n plus 1 things and you want to average them up, then what you do is you take the average of the first n things and you do a convex combination of the average of the first n things with the last thing. And the weights have to be n over n plus 1 for the average of the first n, and 1 over n plus 1 for the last one. So n parts for the first n, 1 part for the last n, which we wrote in this convenient way of take whatever it was before and adjust it by a 1 over n plus 1. And we used this formula to adjust the average as we went for states as we went. Let's see what we have on the blackboard to jog our memory. So this was, let's see if we can find it. Oh, we started with 20 chicken McNuggets. Okay, let's.
That was in the class where the digital blackboard was over.
Okay, good. So it was on the physical blackboard. Okay, very good. So let's write it down one more time. So here was the algorithm. This was what Monte Carlo learning. Monte Carlo learning. And what we basically do is we simulate an episode. So simulate an episode. So what is an episode? It's a sequence S0, action 0, R1, S1, action 1, ... all the way to the n, where it ends at some time n. And then we get the total return, which I sometimes call the total rewards, the total return, which is the sum of the ri's, I going from 0 to n or 1 to n. I guess if you want to discount, you would also put a capital gamma. This is the total return from times 0, from S0, gamma, and you put gamma to the power I. To discount it, we were doing, mostly we always do problems with no discounting, but that's what it is. And then this was the part where we use the update. We say, what is the value of state S0? Well, we should update it so it looks more like this total return. So the total return is sometimes called G. I don't know why it's called G. I think they were out of letters. And then we update V. So we did in our code, we did V of S0 plus equal, and then we did 1 over the number of times we visited S0 times V of S0 minus G. Let's put G in purple, like this. So this was in our code. I guess there should be a plus 1. So where n of S0 is the number of times we visited at S0 before. Number of visits to S0 before this loop. And I guess, you can even make the algorithm a little bit better. You might as well, instead of updating just the first state, you can calculate the rewards from all the things. So let's call this thing, let's call this a G0. Well, in general, you can calculate G sub t, and then you can update state S sub t. Okay. Let's see. S sub t. How many times did you visit S sub t? S sub t plus 1, and then take the old average S sub t and adjust it to be more like G. So this was the learning we did last time. So this is a nice way you simulate the episodes, and then you are adjusting the V's. Then we did the same thing for the Q's. So same idea for Q's. Same idea for Q. Q of S comma A. And then we were learning the Q's. And if you learn the Q's, you can try to improve the policy. That was the next idea. Use Q's to improve policy. And this part had some tricky stuff with exploring, right? You don't want to get stuck. You must do tricks to explore. And that's really what we did last class, but this is the sort of gist of the last few classes on Monte Carlo learning. So today we're going to sort of finish up Monte Carlo learning, and we're going to do more Monte Carlo learning, but it's going to be kind of even more difficult. So this is why it's a good place to to pause for a second and see how the Monte Carlo learning is working. So this is the formula we had before, and it all came from the thing that was on Mathematize a second ago. Yeah, and I think we learned zombie dice. We learned when to roll again or not in zombie dice, which was a nice, fun example. Any questions or comments? Yeah.
So just for Q to be Q of S comma A equals 1 over in whatever Q of SA minus G, right?
Yes, right. So instead of like you visited this state, it's like you were in this state and you took this action. So it's sort of state action pairs become the new like states. Yeah, very good. Yeah.
Would you be able to post that example that you did?
Yes, I can post the what is it? The zombie dice example. I can definitely do that. Yes. Yeah. Okay. So you guys will have the next homework, which will be due in like 2-ish weeks. Will be you guys will do Monte Carlo learning. So I'll give you a problem similar to that zombie dice problem, and you will learn like this if you want, and tell me what is the value of V and what is the value of Q and what is a good policy in some game. To be determined, should be posted soon. Today we're gonna take this and kind of like ramp it up and try to make it even better. And the first thing we are gonna do is something I hinted at, which is we're gonna replace this part of the formula. So this part of the formula, the 1 over ns plus t, we're gonna replace it with some constant called alpha. So I call this constant alpha learning. Let's see what it looks like in Mathematize. So you just replace this 1 over n plus 1 just gets replaced with an alpha, but otherwise the formula looks exactly the same. So you're updating not based on the value of n, but based on the value of this alpha. And alpha will be some small number between 0 and 1. Maybe it's like 0.01 or something, something like that. And the first question I want you to think about in the context of everything we've been doing over here, so in this whole situation, and specifically with what we were doing last class and before, why on earth would we do this alpha thing? So I want you to sort of brainstorm some ideas. What's the deal with this constant alpha? What are some advantages? So in the context of Monte Carlo learning, i.e. slowly learning the best policy by doing Monte Carlo samples, why might the constant alpha update be better than the 1 over n update? What are some pros of doing this constant alpha thing? Okay, and I'll let you guys think for a few minutes. What could some possible pros be? And then I will tell you some of the possible answers. Okay, why don't you think for a few minutes? Feel free to chat with your neighbors. Tell me your best ideas. All right, 30 seconds left. Put in your best guesses. Anything you think of. There are many possible answers. I guess you can also, if you really have no idea, make something fun up. I guess you could say, I like Greek letters better. That's a good reason. Okay, let's see what people said. Constant alpha updates. All right, more change to the, let's read some of these. I don't know, great answer. We can tune the alpha for better, faster convergence. That's an interesting thing. Yeah, so you definitely, if you switch to this constant alpha thing, you're gonna have to play with the value of alpha. So you're going to have to tune it. And yeah, it'll be different. I don't know if it'll be better or faster. That's maybe. Easier to find the policy through consistent change. Okay. There's potentially, so when you do the 1 over n update, the bigger n is, the smaller your updates are. And it's sort of perfectly tuned to give you the exact mean. So this is along the right kind of idea, right? So we're doing something with the constant alpha. Faster adaptation to change in states. So if you want to know how fast the things are changing, you can sort of get the effective value of n by doing 1 over alpha. So we replace alpha with 1 over n. So if you do 1 over alpha, that's like the number you're looking at. So if alpha is 0.1, then it sort of takes like 10 updates to sort of update the full thing. So that's like one way you can sort of understand if it's faster or slower. So whether or not it's faster or slower will be like the relative size of alpha versus what n was. So it can be faster or it can be slower depending on what alpha is, but there is something else that has changed. Ooh, this is a very nice answer. We can give more weight to the recent samples. So this is absolutely true and is a really important consequence of doing the constant alpha. Let's decide if this is a pro or a con, but this is one major difference. So let's write down the before and the after. So the 1 over n learning versus alpha learning. And I think this is the biggest possible difference, is all samples have equal weight, versus if you do the alpha learning, the most recent samples have more weight. And in fact, the how much weight they have is like alpha to the power of how long ago it was, right? So something that's way in the past will have like really, really tiny value. I think this was something on the board. It's like geometric decay. So the further back in time it was, the less we weight the sample. The 1 over n learning weights everything equally. Okay, so this is absolutely true, that it weights the more recent things more. Is that a pro or is that a con? Like, is it good to do that? So like you're weighting more recent things more and things in the past less. Is that good or bad? Anyone want to take a stab? Do you think that's a good thing or a bad thing? Yeah.
It could be a bad thing.
It's a bad thing. Yeah, why is it a bad thing? There's a sense in which it's a bad thing. Why is it a bad thing?
You get like a weird sample, then it'll still.
Yes, that's totally true. So this one, as you learn more and more, everything is like sort of weighted equally. As you learn more and more, eventually, if n is large enough, then eventually the variance goes to 0. So like you get 1 or 2 bad samples that are weird, that's fine. It'll get washed away in the limit. So if you do this, all samples are weighted equally, and therefore eventually variance goes to 0. No individual sample ruins your day. Individual sample matters. So this is totally true, that there's one advantage of the 1 over n. However, there is something actually that is good about more recent samples having more weight. Can anyone think of what is something that would be good about it? So this is true, and this is one thing that's bad about it. But what is one thing that is good about it? Yeah.
It should learn surprising things.
It can learn surprising things. Let's write learn surprising things. I think for the right definition of surprising, this is true. But why might things be surprising? Let's remember how things were going over here. Yeah.
I'm not sure if it's valid, but if we're updating our value function, Q function, more recent samples are based off of like more information in a way, so it's giving more weight to, if we're just simply more correct in a way.
Yes. Okay. So this is absolutely the right idea. So why might things be surprising? Well, as we're doing this journey of learning through simulations, I sort of maybe didn't write it explicitly here, but the value function actually depends on the policy, right? This is one thing we've talked about before. The value function always depends on the policy that we are doing, all right? Like a value function on its own doesn't make any sense. You can't say, what is the value function? You can say, what is the value function for this particular policy? And when we simulate an episode, we simulate it under some policy, pi. right? And that's all fine if the policy pi is always a constant, then nothing will get us. But if the policy pi is changing as we are running these simulations, like we have a big loop and we're learning, especially when we're doing this thing, improving the policy pi is changing as we learn. So the policy on our very first run might be totally random, and we're hoping by the end the policy is actually quite good, right? But that means the policy is changing, and that means the samples of the total return we're getting, these depend on the policy, and they are changing over time as well. And we are hoping that the value function v always represents the policy of the current policy we're doing. So if you're using this constant update rule, it will sort of forget the old policies and remember the new policies. So more recent samples have more weight, and I'd say it's surprising, like a more accurate way to say surprising, learn surprising things. You can learn new things about the new policies. So learn the new policy more. So when the policy is changing over time, you want to sort of, it's a good feature that we forget the past. The past was the old policy, right? A great example is, what was the policy originally? Well, the policy originally was totally random, was some bad policy, and we're hoping to improve over time. So it's like you really do want to forget the things. So that is a big advantage of the alpha learning. We forget the old policy automatically. So this is a feature, and it really is because the policy is changing over time that this is a really good thing to do. It's a bit like if you had a machine that was outputting random numbers, but how the numbers are random changes over time. You don't want to count everything equally. You want to sort of forget what happened 1,000 years ago. That doesn't really affect what's happening now. You want to only keep track of the more recent ones, and this alpha learning is a nice way to do it. All right, so this is a really important idea that we do want to forget. We do on purpose want to forget the past, and this constant alpha learning makes it easy to do that in an explicit way. And like I said before, the size of alpha is sort of our characteristic memory, right? So e.g., if alpha equals 1/10, this is like a memory of last 10 times, 10 episodes. So if alpha is 1/10, you sort of you remember what happened on a scale of like 10 things. If something happened 10 rounds ago, that's kind of the past. If something happened 20 rounds ago, that's even more in the past. And the further in the past, the more we forget it, and the closer it is. This is like the scale of the times that we remember. Okay, so that's a nice idea. Any questions or comments about this idea? There is one other very nice thing about this alpha learning that is even more obvious. Let's see if anybody wrote down the silly obvious thing. So we're going to have to decide what alpha is and change it as needed. This is true. So in some sense, alpha is more flexible than the n, because if you wanted, you could make alpha equal to 1 over n. So you can sort of set your own schedule. So sometimes that's tricky to do, but it does give you more flexibility. More equal treatment for each possible state. Yeah, so I guess the equal treatment is in time or not. Let's see. Weights move towards the present past. Yeah. This is kind of along the idea of what I am going for as the next thing. Less RAM. Decreased complexity of the code. Same kind of similar thing. Cheaper. These are all the same idea, which is saying that somehow the... all right, I think we got mostly these idea. So somehow the alpha, not only is it better in some sense of forgetting the past, but there's something about it that's even easier. What is even easier about the alpha compared to the n? Yeah. That's right, yeah. You don't need this array, n of st was a whole array. It was taking up as much space in our computer as v, right? So the thing we actually want to learn and this like silly thing of how many times did we see a state, they were the same size, and we could just throw it away. You don't even need to know what n is. So this is the other big pro. This is one pro. But the other big pro is that you don't even need to keep track of n, the number of visits. So that's a nice thing. It makes your code easier to write. You do have to sort of replace it with fiddling with what the value of alpha will be to make the code work well. So you're sort of trading one thing for another thing, but this is a nice feature. And the other nice thing about this is it now potentially works even for extremely large spaces. So before, you sort of had to visit every state many times to sort of get a good value. If you do the constant alpha learning, you can kind of hope that even if you don't visit some states, maybe we can make it work. And this is going to lead into our next sort of topic, which was the constant alpha learning allows for learning non-array-based value function. So constant alpha allows for non-array-based V. So I think I mentioned this a few classes ago. This is going to be the sort of next little topic we're going to do, is how do you learn a non-array? So before, we were doing this, V of S with square brackets, and today and beyond, we're going to do V of S with round brackets. And you might think, oh, this is very silly. Why? What's the difference? Well, in your computer, V of S means the state S is stored as one value, whereas here it is computed. It is computed. So the state S is used in some kind of calculation to compute the value of V of S. And over here, it is stored exactly. And this can make a big difference. And specifically, how are we going to make this change? Well, there's also going to be, in addition to S, there's going to be some parameters. And with our love of Greek letters, we're going to use theta for parameters. So we're going to do V of S, semicolon, theta. And the value function is going to be computed as a real honest function in terms of S. I'm going to give you an example of what this looks like. An example. And we're going to do the example I do sometimes, which is chess games. Chess games. So imagine you were trying to learn you were trying to get good at chess by doing value functions. If you did it this way with an array, then you can only learn about a state when you play that exact chess game. So the number of states is astronomically large. It's like 10 to the 100 or something silly. Like it's like more than the number of particles in the universe. There's all sorts of crazy ways you can make a chess game. And your value function V of square brackets S, it literally can only learn if it sees that exact game. If one pawn is moved over, it's like a whole new game. That's how arrays work. The entry for this situation and that situation are two different entries. On the other hand, if you have V of S comma theta, you can make very simple value functions that actually work quite well. Here is an example of a very simple value function of V of round brackets of S. So V of S, what it will be is it'll be like this. You'll get +1 for every pawn that you have. So times the number of pawns in S. And you get -1 for every time your opponent has a pawn. Number of enemy pawns, let's say my pawns, enemy pawns in S. And then you get +3 points for every minor piece. So those are knights and bishops, minor pieces, my minor pieces in S. You'll get -3 points for every opponent minor piece, number of enemy minor pieces in S, and so on and so on. So you'll get maybe, say, +5 for rooks, number of my rooks in S, -5 for number of enemy rooks in S. And then, +9, say, for the queen, plus and -9. Do you have your queen? Number of queens, my queens, and -9 for the number of enemy queens. It can be more than one if you promote your pawn into a queen. Number of enemy queens in S. So this is a nice, very simple function. Even though there are 10 to the 100 possible states, this function, it can be calculated for every possible state, no matter what state it is. Even if it's a state I've never seen before, it's some super weird state, we can calculate this, and it will give me some number that is positive when I'm doing good, and it's negative if I'm doing bad. And just by using this very simple rule, I can figure out how to play chess. I can play some pretty good games. You should combine it with thinking a few moves ahead. But this very simple rule of pawns are worth 1 point, knights are worth 3, rooks are worth 5, and queens are worth 9 is a good sort of rule of thumb. In a more sophisticated version, you could replace these numbers 1, 3, 5, and 9. They could be the parameters. So this is, we could say theta, and we could replace 1. 1 could be theta sub pawn. It's like how much a pawn is worth. And 3 could be theta sub minor piece, knights and rooks. And this is the rooks, theta sub rook. So knights and bishops are the minor pieces worth 3, and the queen could be theta sub queen. Okay, and so this is a function. It's got 4 parameters. How much is a pawn worth? How much is a minor piece worth? How much is a rook worth? How much is a queen worth? And by changing the parameters, you can figure out, all right, better or worse strategies. And the chess grandmasters tell us that it should be 1, 3, 5, and 9. That's a pretty good rule of thumb. They have figured that out by playing many, many games. And so they've sort of learned these 4 parameters. And so this is the big advantage of doing it this way. We can take something incredibly complicated with a huge state space and try to learn, hopefully, a simple function that depends on much fewer parameters that still does pretty well. And we sort of like extract the essence of a game without having to learn every single individual state, which would be impossible. So this is the big idea. We're going to try to learn functions like this. Yeah?
Could you have a theta that depends on the state?
What does it mean for theta to depend on the state?
As in, you could have the value of the bond depend on the state.
Okay, I think what you're asking is, could you, right now, the function that I've written, it turns out it is a linear function of theta. So this function, as written, this is a linear in theta. Why is it linear in theta? It's like linear in the linear algebra sense, right? If you double theta rook, all the things that appear are theta rook times something. So if you double theta rook, all the things that involve it get doubled. I think what you're asking is, could you have a non-linear function? And you absolutely could. Like you could have a function. You could add on something like plus theta. I don't know, theta doubled pawns. No, that's still linear. What do I want to do? Ooh, okay. Let's do one. Let's do a really nonlinear one. Let's do one like this. You see, we got theta pawn over here. So yeah, let's zoom in on that term. So one of the terms is theta pawn, and before it just said count the number of pawns, right? Count the number of pawns. But maybe some pawns are better and some pawns are worse. So I'll do theta pawn, and then I'll multiply it by like the number of pawns, and then I'll do plus like how there's a parameter that's like how far up the board the pawn is. So we'll have another theta. We'll have like theta like how close to promoting. And that'll be like summed over each pawn. I don't know how you want to do it. Times like how far away the pawn is. How far away. And now it's a nonlinear function. And you can cook up any weirdo function you want, whatever you want, you can put it in there. And in fact, the ultimate thing that kind of makes this stuff extremely appealing is you can do this crazy set of functions called neural networks. So more generally, you can have any weird combination, any function. Oh, I don't know what that is. Any. It made it ginormous. That's not good. Am I back to small? Okay. Any function. And a neural network is an example. So you could input over here. You could have inputs, which are like, where are your pieces or whatever. And then the thetas, instead of being numbers, they are weights in the neural network. And they do this like big, crazy web of computation. They do all sorts of weird calculations with nonlinear functions and whatever, and layers and weights and biases. And then at the end of it, they come out, there's some huge computation. At the end of it, they just come out with some number v of s, which is the input, comma, theta, which is kind of the weights and the biases in the middle. So you can do any function you want. This is just to give you an idea of a simple possible function and why it takes us from something that we couldn't possibly learn because there's too many states to something that we can learn because we have a function that applies to all the states. And then the question is just now, can we figure out good parameters that make it work? Great question. Any other questions or comments about this thing? Okay, so how are we going to do this? We have to learn sort of like how we take our rules that didn't have parameters and how do we start to work with the parameters. And the very first thing I'm going to show you is a very simple and easier question, which is how do we make the parameters do what we want? So how do we work with parameters? How do we work with parameters. If you've taken a statistics class, you might remember this from things like linear regression, finding parameters that fit the data that you have. So this is the very first question that I'm going to answer. Before, like if we had, if we had three states, v of 0, v of 1, and v of 2, if it was very simple, and we were like, how do we set v of 0, v of 1, and v of 2 to the things that we want? Then it's very simple because you just set it, you can set each one directly. So this could be the value at 0, let's say y0, y1, and y2. So that was trivial before, but now it's a question. So now the question becomes, given 0, comma y0, 1, comma y1, 2, comma y2, how do we find theta? How do we choose theta? Choose theta. So that what? So that v of 0 is approximately y0, v of 1 is approximately y1, and v of 2 is approximately y2. And I guess the important thing is the thetas. Let's put those back in red again. V of 0 comma theta, v of 1 comma theta, and v of 2 semicolon theta. So it depends on theta. So before we could just say like if you have three values, you just shove them in your array, you're done. But now it's like, how do you pick the parameters theta to make it follow the values you want? So it's a nice idea, but how are we going to actually do it? Okay, and I'm going to show you in the code. If you have seen this kind of thing before, it'll be a nice recap, but maybe you haven't seen this kind of thing before. Questions or comments before we move to the code and start seeing how we're going to teach a function, how are we going to find the parameters theta that do this with the values that we want? Okay, let's go to the code. All right. Okay, and I have prepared this, but let me make a new file that I will run from scratch so that things are simple. And it's not too complicated. So the first secret is we're going to use a package called JAX. And JAX is just like NumPy. In fact, it has something called jax.numpy. So it's import jax.numpy as JNP, and every time you were using NP before, now we use JNP. Very occasionally we need the JAX itself, but that's what it's called. And I'm going to run it, and it'll import it just like NumPy. And the first little thing I got to show you is one annoying thing about JAX. So it works almost exactly like NumPy, but there is one annoying thing, and I'm going to tell you guys the annoying thing up front. So in NumPy, you would just have like the y values, and this was in, let's do this in NumPy, not the j values, the y values in NumPy. Oh, I guess I better put in NumPy as well. Import NumPy as NP. And the y values, they could be np.array, and you could do 1, 2, 3. Okay, very nice. What is it like in JAX? Y values in JAX. Well, actually, it's exactly the same. JNP. So what is the annoying thing? This does exactly the same thing as this. You can make the array. Here is the thing that is annoying. Suppose you want to change the value. So suppose you want to change the value of the last entry, the 2 entry. You want to change it to 7. You're like, okay, please make it equal to 7. That's no problem. You put it in the computer and you're like, set the 2 value equal to 7, and the computer is like, hey, that's totally fine. Y values in NumPy. And it's like 1, 2, 7. Great, we changed it to 7. Now let's try to do it in JAX. Y values in JAX of 2 equals 7. And we run it, and now the computer yells at you. And you're like, oh no, I just did something so simple. Why does it work? And the reason is sort of explained here, this complicated thing, but the object does not support item assignment. JAX arrays are immutable, not mutable. So mutable means you can change the values, and immutable means you cannot change the values. So there is no way in JAX to change one entry of an array. If you want to change it, you have to change everything. So the thing that you would do is if you want to set the value to 7, you would say, okay, let's leave that as an instructive little error there. You would say y values in JAX, and you would say equals jnp.array of 1, 2, 7. So you sort of have to give it the entire array again, and then that's fine. Now I've effectively set it to 7. There's a little shortcut for this, which is you can do y values in JAX. You can say, please make it the same thing as before, but set the entry in 2 with dot at 2, set it to 7. And this is effectively, we'll make a JNP.array of 1, 2, 7 by taking a copy of y values and setting the thing to 7. So this will run no problem, and then now you have the thing. Okay, y values in JAX. And so now it's 1, 2, 7. Okay, so this is the annoying thing about JAX. So you'll occasionally see me do something weird like this. But this is the price you have to pay to use JAX instead of NumPy. And I will unveil to you slowly the miracles that JAX has that NumPy does not have that make it worth this price. But any questions or comments about this is like the downside. This is the price you pay. Okay, but now we can do the fun thing. So let's try to find some parameters. And I think we had some x values and y values in my example. So let's finding good parameters. And this part might remind you of a statistics class where we have some x values. And I think I made the x values, I made them 0, 1, and 2. Actually, let's make it a little more exciting. Let's make some of them negative. Let's make them negative 2, 1, 2, and 3. That's very nice. And let's make y equal jnp.array. We'll make that minus 3, 4, 8, and 10. And the question is, how do we find a function? How do we find a function v so that v of x equals y? And if v was with square brackets, it would be very simple. V of minus 2 equals minus 3. V of 1 equals 4. V of 2 equals 8. V of 3 equals 10. You just plug it in by fiat, but we're doing it with parameters. So v of parameters like this, and we'll use theta for parameters to make it work. All right, and I guess let me start by plotting them. So I have a little plot command so we can see. Plot is not defined. Let's import the plot. Import the plot. All right, so here are our points. And we're essentially, if this was stats class, we'd be saying, find a function that goes through these points. That's what we're doing. Questions or comments so far? Here is my method. I'm going to pick a class of functions that you're very familiar with, which is called a linear function. So I'm going to just have theta for now is going to be one single number. And I'm going to do it like this. F of x comma theta, what will it be? It'll be super boring, theta times x. Theta times x. And what this does is theta is just the slope. So for example, if theta equals, let's make it 1.5, then we can plot the slope. So we can plot dot plot, plot dot plot. I have to tell it the x values and the y values for this to work. So the computer is suggesting x comma f of x theta. That would tell me the points at exactly the x values that we had. I want all the x values. So why don't I make an x-axis, and I'll do f of x-axis comma theta, and I got to tell the computer what is the x-axis. So the x-axis will be all the points, say, between minus 5 and 5, 100 of them. So very nice little thing. Let's see if this works. Okay, so now it's plotting what this thing is. We can maybe label it. Label equals, this is the function f, and then this one is the data, the x and the y, and I can make it, I'll put everything with plot.legend. Okay. Okay, there we go. So that's what we got so far. Is it matching well? I don't know. You tell me. Questions or comments so far? Yeah.
Could we also include an intercept somewhere?
You could include an intercept. If you want to include an intercept, then theta can't just be a number. Now it has to be like a vector. But yeah, why don't we do that? That'll be fun. So let's make it theta of 0 plus theta of 1. And now if I run it, it's going to yell at me, and it's going to be like, hey, you can't, if theta is 1.5, how can you do 0 and 1? But you can make it an array, jnp.array, and we can make it 2.0, comma 1.5. And now it should work. So now the intercept is 2, and the slope is 1.5. Yeah?
Also, if we set an array like you're just doing, like on y is equal to square brackets,
Yeah.
Like, once you see, is whatever we're gonna do with GMP, is that gonna matter? Something like that? Or if we use like, if we put NumPy and use NumPy arrays instead?
Yeah, so far everything I've done so far could have been done in NumPy. There's going to be one crucial step when we will get to, and I will say now is where the magic of JAX happens, and it'll be a thing you cannot do in NumPy. That has yet to come, but yes, keep your eyes peeled. That is coming very soon. Yeah, great. So this is great. We got the theta, and then we can play with the theta. We can be like, hey, let's try to make the slope a little bit more, 1.9, and run it again. Oh, that's pretty good. Maybe I can make the intercept a little bit less, -2. Ooh, that was worse. Let me try making the slope bigger. Okay, so we have, okay, I just gotta add a little bit here, and I'll be in great shape. 1.7. Oh, maybe a little bit more. We go up to 1.4. Okay, we're getting close. So the general question is, we have this picture of the line, the function that we're thinking of, and the points. And the question is, how can we find the values of the parameter that fit the data well? That's the question now. And this is one you probably have seen before, so I want to see what is your opinion on this. So I have made a mathematized question. Improve the parameters. How do we improve the parameters theta? So you have the picture, you want to make it better. How do you make it better? How do you even measure if it's good or bad?
Are we assuming the linear function, just a general?
If you want to assume the linear function, you can. But yeah, the question in general is good to ask as well.
There might be an extra answer because I'm gonna update my answers.
Okay, sure.
They're gonna after.
All right, just under a minute to tell me your ideas. How can we improve the parameters theta? Okay, tell me what you think. Let's see, how do we improve these parameters? Okay, let's take a look. How do we improve them? Ooh, my goodness, amazing. Okay, very nice. I'm seeing some good things from stat class, like MLE, minimize, RSS, larger, smaller. Let's see what people are saying. I guess I want to look at the submissions. Okay. Trial and error. This is like the first idea. If you're going to do trial and error, you do need one ingredient that I haven't mentioned yet. Let me see if somebody has mentioned this ingredient. The sum of the residuals. Yes, this is the right kind of thing. So the thing that I should add to what I've done so far is I should have some kind of numerical value that tells you how good or bad it is. And this is often called the loss. So let's calculate something called the loss. I'm sure if I type in loss equals, Google will tell us the formula that we need. Loss equals, there we go. Okay, what did Google put in as the loss? It says do f of x comma theta minus y squared. So f of x comma theta is what our line, our blue line, thinks the value is. Y is the true value, and we do the difference squared. This difference is sometimes called the residual. So f of x minus y is called the residual. The residual squared, and then you sum it, is sometimes called the residual sum of squares. So if you wrote RSS, you were doing this loss. This is sometimes called the square loss. The square loss. Sometimes you'll do it with a mean instead of a sum to average over all the points so that it is not growing or shrinking as you shrink the number of points. And then it's the mean square loss or the mean square error. So that's a very nice thing. We can print that out. So then we can have a number that tells us how good we're doing. Actually, why don't we put it in the title? Oh, yeah, there we go. So it's 11.035 now. And now I have a method. I can try to make it better or worse by moving it up or down. So why don't I move the intercept up a bit? And now it went down. It was 11 before. Now it's only 8.5. So I'm getting better or worse. And now that I have a numerical way to do it, I can at least do guess and check or trial and error. So that's a good thing. The mean square loss should remind you of something from stats class. Although sometimes in stats class they just tell you, they skip the step of telling you what you're doing and you just do it. So maybe you doesn't ring a bell, but now you know. So that's the mean squared error or the mean squared loss. Questions or comments about the mean squared loss? So some people are saying minimize that. Okay, great. Let's see if we can get more specific. Yeah.
What would happen if you like say the mean absolute deviation instead?
Yes, this is a good point. You could also do that. And in fact, the way we're going to do this, you can put in any function you want. This is just a nice one. One nice thing about this one is the squares are nice. Everything will be like Pythagoras if we do this one. So this is the one people like. You could do anything you want. And for what we're about to do, you put in any weirdo function that measures how good you're doing, and it will be fine. Yeah. Okay, but let's see other people's ideas. So minimize the sum of residuals. The sum of residuals is not a good idea, but the sum of the residuals squared is. The problem with the sum of the residuals, if you're overestimating and underestimating, it'll cancel out. It'll be like, this is the classic joke. Okay, so 3 statisticians go out on a hunting trip, and they see a duck. And then the first one shoots to the left, and the second one shoots to the right, and the third one goes, we got him. All right, so this is not what we want. We want to minimize the sum of the squares so that if you're left or right, they're both bad. Okay. All right. Now this is a nice specific thing. Iterate over parameter space using the gradient. The gradient. So this is using the gradient. Let's see who else did anybody else write gradient. Least squares. So again, least squares is like find the least is like find the minimum. Squares is like what we're doing. The question we're answering is how do you find the least squares? So minimize the sum by what? I don't know. Yes, very, very honest answer there. Yeah, great. Minimize, iterate something. Very nice. Error is measured using L2. L2 is this square thing. Cubic spline. Cubic spline is telling you the type of function. So we're doing linear, not even cubic spline. I guess a lot of people are fans of cubic splines here. Okay. Least squares. Yeah, least squares. How do you find the least squares? Okay. Okay, so this is what we're gonna learn. How do you find the least squares? And I'm gonna draw it as a little cartoon. So you should imagine that the parameters are the x-axis. So this is for this picture, the parameters theta are going on the x-axis. Of course, in real life, the parameters are multidimensional, so you can't draw them on the x-axis because the x-axis is only one-dimensional, but you just have to use your imagination. And on the y-axis, I'm going to plot the loss. The loss is like how close we are, how bad we did, right? So we want to make the loss smaller, and for every value of the parameters, we have some loss, right? So when the parameters are set a certain way, we can figure out what the loss is. So the parameters, it's something. So in fact, like as an example, if we go back to the code that I had up a second ago, when the parameters were equal to, what were they? Minus 1.0 and 2.9, the loss was 8.59. So when you are at this point, e.g. at negative 1.0, when theta equals negative 1.0, 2.9, the loss was 8.5, or whatever it was. So like at every value of the parameters, we can calculate the loss, and we could just do like guess and check. Like we could say like, we could try parameters over here, a little bit higher, a little bit lower, and we could plug them in and see if it's better or worse. We could plug in a bunch of values. That's the kind of thing we can do. So we're kind of like building up a picture, what does the loss look like, and trying to find the parameters that are good. And you can kind of think that behind the scenes, but we can't see it, but behind the scenes there is some function here that is living there, and we want to find the minimum of this function. So there's some secret function we can't see because we can only plug in one value at a time. If we could see the whole thing, then we can maybe find the minimum. And this is the big idea that has driven a lot of progress in statistics and machine learning and things, is one really convenient way to kind of visualize the secret function and find its minimum value is to use the gradient. So this is the big idea. I'm going to draw a crappy light bulb. Ooh, a giant light bulb. Okay, amazing. Here's my giant light bulb. That's like too big to see. Okay, giant light bulb. Here it is. Use gradient. So what is the gradient? The gradient is an arrow. So if in addition to the value 8.5, we could get the gradient going down this way, if we sort of knew that the function was decreasing in a certain way, it would steer us, and we could try as our next guess. We could try this point over here. So if we knew the gradient, we knew which way the secret function is decreasing, then we know what to try next, and hopefully it is less. And then if that keeps up, like if this function really does look a certain way, we can try the gradient again and again and again. So this is called gradient descent. This is the gradient descent algorithm. Gradient descent. And this algorithm is the secret sauce behind machine learning. Everything is trained with gradient descent to find the minimum. Find the minimum. Okay, of the loss function, of loss. Okay, so that's the idea, and that's the secret we're going to use. And this is why we are using JAX, because JAX has a function called JAX.gradient that does the gradient. So let's go back to the code. So how do we find the gradient? We're going to do it with JAX.gradient. And to show you what JAX.gradient looks like, let me do a little example. JAX gradient examples. And we're going to do the very first function you can think of taking the gradient is the square function. So here is a function, x squared, very simple function, that does squares. If I asked you to do the derivative by hand, I'm sure you could do it, but I will not ask you that because, watch this, look at this magic. What is the gradient of the square function? JAX.grad of square. JAX.grad of square. And that will do the derivative for you. Okay. Boom, we did it. What did it actually do? It made a new function called grad squared, and grad squared is now a new function. So it's as if I had typed in definition, grad square, the gradient of the square function, the derivative, and I had returned 2x. Of course, it does this automatically, so you don't have to do this. It's already done for you. So for example, if I do the grad square of, 7, it should return 14. Let's see. Okay, 14. Look at that. We did the derivative. You're like laughing because this is so silly. You could have just done it by hand. Why are you torturing the computer to do it? Well, the computer can handle it no matter how complicated it is. So let's make a more complicated function. More complicated function. And let's make it depend on a bunch of things. So I'm going to call the things x vector. When you do JAX.grad, it will assume the 0th entry is some kind of vector, and it does the gradient with respect to that. What should our function do? I don't know. Let's do some complicated stuff. The 0th entry times the first entry plus the second entry to the power 7 plus, I don't know, np.cosine. I guess it has to be jnp. jnp.cosine of the third entry. Okay, there we go. So there's a really stupid, crazy function. All sorts of weirdness going on. I guess this function isn't so bad. You could have a first-year student eventually calculate the gradient, but let's do it our way. So let's make the vector jnp.array 1, 2, 3, 4. Say, actually, I should make the last entry something with pi. jnp.pi. Yeah, that's very nice. Okay, and then we can get the gradient, and it'll just calculate the gradient for us. And it's telling us the gradient is 2, 1, 5.1, 8.7 times 10 to the minus 8. So what did it do? What is the gradient? Well, so if you do the gradient, that's doing the derivative sort of with respect to these things, and it's outputting a vector, and the vector is like the partial derivative with respect to each one. So it's saying the derivative with respect to x0 is 2. And that's because x0 only appears in this first term. And so you take the derivative, you get whatever you plug in here. So if I change this 2 to a 22, it will change that 0th entry to a 22. This is a bad example. Let's make it a 7. Okay, look, it changed that to a 7. That was from this term over here. What is the derivative with respect to the second term? Well, that's x0. So that's whatever is over here. So I change this to 5. I'll get 7, 5. Okay, great. And then this next one, I get 7x2 times 10 to the power 6, which is why it is this crazy number over here. Let's make this exponent a little bit smaller. Let's make it a cube. So we should get 3 times 3 squared, also known as 27. There we go, 27, 2.7 E1. And last but not least, I got the sine of 0, or sine of pi, which the computer says is very close to 0. So there you go. It can do all sorts of complicated derivatives. No matter what function you put in here, as long as it's like a differentiable function made of differentiable pieces, JAX can do the derivative for you. All right. And this is the reason we need to use JAX and not NumPy. You cannot do this in NumPy. You have to use JAX. Behind the scenes, it's doing all sorts of crazy stuff. It is making something called a computational graph, which is how is this computed and how does it depend on all the pieces, and then it's using something called backwards propagation to find the derivative over here. But for us, very nice. You just run it and it does the gradient. Yeah?
What happens if we make x back a normal Python array instead of a JAX array?
That's a great question. I think it just won't work. You want it to make it a NumPy array?
Or maybe just as an array, just remove like we just do like square brackets.
Okay, so like a list. So this is a list in Python. I think for sure it will yell at you if you do this. Let's see. Yeah, there you go.
So what if we do a NumPy array?
Okay. You do a NumPy array. I think it will also yell at you. Because it'll be like, I don't know how to deal with this. What is this NumPy thing? It might automatically convert it. That's the only thing that potentially can happen. Okay, there you go. It still worked. So I think what happened is it converted it. So it tried to convert it. Yes, very nice. Okay. Questions, comments, how the derivatives work? Yeah.
So what happens if you have like if statements or for statements?
This is great. Sometimes if you put in if statements and for statements, it'll work just fine. There's certain things you're not allowed to do. And mostly they are like things that depend on the length. So if you have an if statement that's like, if the length of x vec is this much, do this thing. If the length of x vec is this much, do this other thing. Then I think it will yell at you. But you can do certain things. Certain things are not allowed. But for the most part, any reasonable function like this will be fine. Yeah.
Also, for defining a function to use the JAX.grad thing, does the function have to define using JAX.numpy, or can be defined using numpy?
I think you should define it with JAX.numpy. If possible, it will convert things.
Okay.
So regular NumPy and JAX.numpy are like sometimes compatible, and you can like just like turn one into the other, and it will sometimes do this automatically, but sometimes not. Yes. Yeah, but okay. For example, I think if we do things like if x vec of 0 is less than 3, then do this, else return. I don't know. Yeah, sure. This. I think this will work. This will be fine. Yeah, it still does the derivative, and for the values I put in, the derivatives were in this branch, the 1, 1, 1. Whereas if x vec 0 is less than 3, something funny is going on. I gotta make this a JNP and not take crazy suggestions from the audience. Okay. Oh, you have to rerun it. Okay, that's what you have to do.
Also, if we put in a vector like 2, wouldn't it just scrap itself because we're trying to vector back 3 on the second page?
Well, I mean, it did work. So, well, okay. Anyway, doesn't matter. Hey, you can do derivatives. Why is this fun? Well, for us, we can do the derivatives. We just have to tell the computer what the loss function is. So we tell the computer, hey, this is our loss function. So how to optimize. So you tell me the loss function, which I already told you what it was, the mean of the value of f minus this, and then you just do the gradient. And now, if you run this, you can do the gradient of the loss function. So you do grad loss function. Remember, it inputs the value of theta, and that will tell you how to change the values of theta. So theta is right now is equal to whatever it was before, -1, 2.9, and this gradient tells you that in the picture we drew before, the direction you want to go is this -5.7, -3.9 direction. So what we have done is we have calculated this direction in the picture, this little blue arrow. And if we update the parameters in this direction, the gradient should go down. Actually, the gradient normally points up, so you got to go the negative of that to point down, but that's what we're doing. So here's my little thing I'm just going to make. Let's go back up to the picture so we can plot it again. Actually, okay, I'm just going to copy and paste my nice plotting, which does all the things that we wanted. Okay, yes, here, let's copy and paste this over. This is just doing the gradient descent with plotted nicely. Okay, so there's some stuff to make a random key. JAX also has some, you have to use random keys when you make random numbers. I guess I want it to be 2 numbers. So I started out with 2 numbers, and then I make this learning rate, alpha, and then I'm going to update it 5 times. TQM, grad loss, what did I call it over here? Grad loss function. Okay, great.
I think you also need to load it in TQM.
And it also wants me to do for the nice little bar, and let's just do 2 iterations to start, and let's plot always. Okay. Let's see if this works. What is it not like? Plot. Function values f of x values theta. We don't have an x values. We have an x values. We have a f of x values. It doesn't like that I'm calling the function f. Do we have a function f? F of x theta. Okay. Why? What does it not like? It doesn't like something. Okay, what were we plotting before? Let's just copy paste that. Plot x-axis theta. This was working fine. So let's try that. Plot. I'm missing a bracket. That's okay. There we go. Okay, so it did 2 iterations, and let's have it output who's who with plot.legend at the end, and let's try it again. Function f, iteration, iter. Iteration I. Okay, here we go. So we started out with the orange line, then we did 1 step, and now we're on the green line, and the green line is better than the orange line. Let's do more than 2 steps. And the secret is we moved in the direction of this gradient. So this little gradient descent line, this is the secret sauce. Theta, you take alpha times the gradient, and you just move in that direction. It's gradient descent, so we're going down with a minus. So theta is getting updated to go down in the direction that we want. So it's like doing 1 step of the little dopey picture I drew. We started somewhere here. We did 1 step. We improved it a little bit. Let's try to improve it again. Okay. Here we go. Let's do more iterations. How many iterations should we do? Let's do 10. And watch it go. Okay, so there you go. We started out at this orange line. Then we went to the green line. And then we went back a bit. Like we overshot. We kind of corrected a bit. Let's also plot the loss. The loss is the loss of theta. That'll tell us how good we are doing. Let's make this label a little bit more helpful for us. Now it really doesn't like me today. Loss function. Okay, yes, I can handle that. Loss function of theta. Okay, so on our first iteration, the loss was 14. Then it went down to 3. Then it went down to 1. Then it went down to 0.6, 0.4, 0.3, 0.31, 0.28, 0.26, 0.25. So every time we're tweaking this line a little bit, it's getting more and more accurate, and the loss is going down. If we kept going and going, eventually it would sort of reach some plateau. This is going to look like a horrible graph, but maybe we'll see that smallest number. It got down to 0.241, and the graph is way up here. Okay. Very nice. So, and there is a limit. There is some setting of the parameters that is as close as possible to those dots. The dots don't necessarily live on a straight line, so there is some minimum value. So what we've done is we have sort of moved in the direction, and we have found the minimum. So maybe the secret true function that we can't ever see in real life looks like this, and we found getting close to the minimum over here. Okay, so that's the gradient descent algorithm on data, just like in your stats class. Okay, and the magic of this thing, I think, really is this gradient function. The fact that you can do this means that you can do kind of anything. As long as JAX can calculate the gradient, you can always do this. For straight lines in your stats class, you also learn some special formulas that work for straight lines. In a second, I'm going to mess with the function and make it not straight lines, and we'll get some cool things working. And the code is exactly the same, so this is the beauty of JAX. Yeah?
So for delta y's are other types of data that we use in stats, like let's say count data or like binary data, can we also use the methods like root of least squares to estimate them instead of this?
Yeah, okay, so I guess, yeah. So far, what have we done? We have made a function f, which happened to be a linear function, and we use gradient descent to find the values of parameters that are good. The method that we use does not depend on the function being linear. So let's put in, actually, let me do this. Now, I came up with a dopey example. You know what, why don't I just move this one over here, okay? Here. So here was the function that I came up with. F of x comma theta is, it's some combination of ReLUs minus this grid. It's a sum, it looks like this. It's a theta I times x minus x star I plus, some people call this a spline. So for the cubic spline people in the crowd, this was my function. So it's some kind of weird sum of things. And if you run it, you get, this is the copy paste of the code that we had before. You get a picture that looks like this. So what is the cubic spline doing? Well, it's not I should stop saying cubic spline. What is the spline doing? The spline is sort of like piecewise linear, and the thetas represent the slope on each of the pieces. So the function is gluing together a bunch of different slopes on each piece of the x-axis, and you can see it working here. You get these weirdo functions, and we started out in the orange at iteration number 9 with a loss of 2, and then 10 iterations later we got a loss of 0.3, and then it got all the way down to a loss of 0.01, where it's sort of like fitting these points perfectly by finding the slopes that go between. And this is, I think, the amazing thing is in stats class, you could not analyze such a function sort of like theoretically or analytically, because doing the derivative and like figuring out what are the values of theta that work is quite complicated. But telling the computer, just like do it, it works because we can do the gradient. So as long as you can calculate grad loss, which is done with jax.grad of the loss, then you're good. And the function, the function is here. So as long as you write these things down, it always just works. Okay, things can go wrong. If you make the learning rate too big or too small, it will explode. Let's go back to the linear case. Let's see what would happen here if I make the alpha, instead of 0.15, I make it 10.15. So it says the loss is man, not a number. And if I go to my plot, you'll see that, first of all, the scale of this plot is on the scale of 1e38. And second of all, you'll see, so at iterations 0 through 7, those were sort of fine. Iteration 0, the loss started out really big. Then the iteration 0 through 7, the loss got down to like 3.4, 3.1. And then at iteration 9, the loss became inf. So what happened is I made the learning rate way too big. And so the picture, which I wanted it to look like this, you have the function, you kind of smoothly go down to the minimum. If you make the learning rate too big, then you, instead of taking a cute little adorable step in this direction, you step like this, and you go into some weird part of parameter space where I don't know what the gradient is doing, and you can sort of spiral out of control and end up with parameters that are infinity. So it does work, kind of in some sense magical, but you still have to work hard to make these learning rates, these alpha values, the right size to make the steps do what you want them to do.
Could you also change the alpha over time to do like a sort of like simulator of the depth?
Yes, absolutely. Yeah. So you don't necessarily need to always have a constant. You could change it. That's called making a schedule. Very often in real life, there's something called an optimizer that sets it for you. But in principle, this is what we're doing. Yeah. Okay. So this is like sort of an introduction to gradient descent, and like making gradient descent fit. If you know the values you want the function to fit, how do you do it? Useful in stats, useful in all sorts of things. In our course, we don't know what we want the function to be, but we do know like the rules of the game and the V's and the Bellman equation and the Q's. So we're going to see how can you use gradient descent in our setup to make the V function do what we want. So, and I will write down one thing, and then we'll do some examples next class. So this was what we did last class. V of square brackets S plus equal alpha times V of thing minus G. Let's here. Let's write this down. We can do a nice before and after. Before V of S plus equal alpha times V of S minus G. So you simulate the return, then you update V like this. After, this was going to be with gradient descent, so now we're going to have V of S comma theta is the thing. And we're not updating the V directly, we're updating the theta. So theta is going to get plus equaled. What is it going to get plus equaled? It's going to be alpha times V of S comma theta minus G times the gradient of V. So this is going to be the update rule. We're going to update the parameters. It looks very similar to before, so we're doing still V of S minus G, but there's this extra term, which is the gradient. That makes the sizes work. If you want to justify why this is true, you can put a loss function, which is the square loss of V of S minus G squared. We'll do more of this next class, and we'll see some nice example where you can learn. So we're going to take this Monte Carlo learning and do the same Monte Carlo learning, but do it with parameters instead of arrays. Okay, questions or comments about this? Okay, let's stop there. We'll do a fun example. We'll learn some parameters. We'll do that next class. Okay, see you guys on Thursday. If you haven't submitted the homework yet, make sure you do it before tomorrow at midnight.